Okay. So we're going to be talking about forces a lot. Normally in physics, forces are a really big deal. We're talking about, the majority of physics is talking about how forces affect the motion of an object. And really what we're trying to do with physics is understand mathematically why things move. And forces are one way to look at that. So a force is any push or pull that acts on any object. And what a force is going to do is it's going to change how that object is moving. So if I have an object moving left to right and I push it, it's going to speed up if I push it to the right, right? If it's already going that way and I'm pushing it that way, it's going to speed up. If it's moving left to right and I push it the opposite way, I'm going to slow it down. And if it's moving left to right and I push it this way, it's going to change its direction. And anytime I'm pushing it, I'm exerting a force on it. Now, in physics, the units are going to be newtons. In physics, there's 4 fundamental forces. So 4 forces that every other force comes from. And really for us, we're going to think about just these 2. And honestly, only one of them we're going to explicitly talk about. So we've got gravity. So gravity is obviously what makes things fall down. It's what holds things down to the surface of the earth. Then we have electromagnetism. So electromagnetism is going to be the force that holds electrons and into atoms, right? It's that positive charge from the protons in the nucleus attract the negative electrons orbiting around. So electromagnetism is basically the force that kind of makes all the chemistry work. And then the fact that I can't put my fist through this table here is because of electromagnetism. The atoms repel each other. I can't put my hand through solid things because of electromagnetic repulsion. And then we've got 2 other ones, the strong and weak nuclear force. So the strong force is, well, when we talk about inside the atom, we've got a ton of protons right in the center. If protons want to repel each other because they're all positive, there has to be another force that's pulling them together, and that's the strong force. So the strong force overcomes the repulsion between protons, and it's what holds the nucleus together. The weak nuclear force is what is responsible for any type of radioactive decay. So when we talk about radioactive decay, alpha and beta decay, that is due to the weak force. Now, when we talk about types of forces that we're going to run into in our day-to-day lives, we've got a couple here that going to be pretty obvious. So we've got weight. Weight is the downward pull of gravity. Any object near anything that has an appreciable mass is going to feel a weight, right? So normally we would talk about all celestial objects, all objects above a certain mass are going to have an appreciable amount of gravity, but everything actually has an attraction due to every other thing due to gravity. When we talk about weight, that's going to be something falling down to the surface of a planet or a moon or a star. And then that force of gravity actually extends out really, really far. When we talk about the gravity from the Earth, the Earth's gravity is what keeps the moon orbiting around the Earth. So it's not like the Earth's gravity stops at the top of the atmosphere. The Earth's gravity keeps going on out beyond the moon. Next thing we want to talk about is the normal force. The normal force is the upward push from a surface. So if I put my pen here, well, gravity's pulling it down, but since it's on a table, the table surface pushes it back up and cancels that out. So that's the normal force. Now that normal there is not normal as in like ordinary. That's a mathematical definition of normal, which means perpendicular in 3 dimensions. We also want to talk about friction. So friction is a force that acts backwards on any moving object, so opposite the direction of motion. And it's any time that an object slides. So if I slide my pen, it comes to a stop because of friction. If I had a frictionless piece of paper, I'd push this and it'd just keep moving slowly at the same rate. Kind of like an air hockey table. When we talk about tension, tension is any pull from a rope. So if I connect something up to a rope, its tension is what's acting on it. And then the buoyant force is any upward force acting on an object in a fluid. So buoyant forces make things float. So buoyant force is what keeps a ship floating in the ocean. Buoyant force is what keeps a hot air balloon up in the sky or a regular balloon up in the sky. But even if your ship sinks, it still has an upward buoyant force acting on it. It'll be lighter to pull up something that's submerged in water than if it was on dry land. The last thing we want to talk about is the net force. So the net force is the total force acting on an object. The net force is going to be the one that determines the motion, because if I have something like weight pulling down and normal force pushing up and they're equal and opposite, pen's not going to move. But if I have a total net force acting on it, that is going to make the pen change its motion. So when we think about net force, we want to talk about something called a free body or force diagram. Now, a free body diagram or force diagram is really easy, and basically they just show all the forces acting on that object. So first off, we draw the object as a box. Doesn't matter what it is, we draw it as a box. There we go. If I'm doing me sitting in my chair right now, that's me. It's a self-portrait. Then we're gonna add arrows from the center of the object that represent the forces. So what forces are acting on me as I sit in my chair? Well, my weight is pulling me down. And then, oops, I did my weight too big. No, I didn't. Who am I kidding? Anyways, then I've got the normal force from the surface of the chair acting up on me. Now, my weight and my normal force are equal and opposite because I'm not falling down through my chair. So the free body diagram would look something like that. Okay? Now, I've got a couple free body diagrams that I did here. So real quick, try to figure out what the net force would be here. So pause the video, give yourself... Yeah, that was enough time. So these two are acting in the same direction, so the net force here is just going to add up. So 10 and 15, we're going to get a total of 25. Okay, for the next one, what if they go in opposite directions? That's right, if they go in opposite directions, it's going to be, well, 15 this way and 10 this way. This should be 5 newtons. Oh, we should also say which direction it's going, and that's going to the right. Same over here. So these are both going to the right. Now, how about that one? So the right answer for this one is actually 18. Because if I add these two together, I'm going to get an arrow that goes like this, right? Because we're going down and we're going over, and now I've got basically a triangle, right? I've got one side, another side, and the hypotenuse. So if I figure out what this is, I would use the Pythagorean theorem. So Pythagorean theorem is a squared plus b squared equals c squared. So 15 squared plus 10 squared is equal to this hypotenuse squared. So F net squared. So to find what F net is, I would do the square root of 15 squared is 225, 10 squared is 100. So the square root of 325, and that's going to get me like 18 and some change newtons. And that's going to be acting down to the left. So that's forces in about 10 minutes.